Welcome to Massive Open Online course on fluid flow operations. In the previous lectures, we have discussed the flow in water channel as a part 1. There we have discussed how the flow will be flow is flowing through the open channel with different cross sections, round in shape, and also cross section will be the rectangular and other shapes. So, in this lecture, we will be continuing this flow in water channel. In this case, we will discuss the equation of energy and discharge of the water channel, and also what will be the critical condition for which that at a certain velocity that flow behavior will be changed, and also at a constant discharge what should be the critical velocity at which the flow condition will be changed for subsonic to supersonic condition or subcritical supercritical condition. So, in that case we will again be considering that energy equation for calculating this optimum condition of the velocity for changing its flow behavior from subcritical to the supercritical condition. Now, what we have discussed in the previous lecture, that the channel where a stream of water flows with a free surface exposed to the open air, it is called the water channel, and the channels have such large hydraulic mean depth, so that the Reynolds number will be too large, and also of course, for that large Reynolds number the flow should be turbulent in condition, and at such turbulent conditions, that is at higher Reynolds number, the friction coefficient becomes constant and is determined by the roughness of the wall there. And also we know that in the channel for different cross sectional area, the flow behavior will be changed, and also the characteristics feature of that flow will be changed in the channel. Now, we will see what should be the total head whenever fluid will be flowing through the open channel. We know that there are many channel that is open, there will be some problems that can be solved using equation of energy. We have already learned about the equation of energy like Bernoulli's equation and conservation of equation, based on which we are getting three types of energy. One is pressure energy, another is velocity due to the velocity, and also the gravitational energy there. So, there are three types of energy will be summing to a constant value, and in that case if we know that particular part of that energy, we will be able to calculate other part of energy between two sections of the pipe or channel sections there. And in that case generally this energy equation sometimes is represented by in terms of head. So, in that case what should be the total head of these three energies? One is energy due to the velocity, and energy due to the pressure, and also what will be the energy due to the gravity, or you can say potential height. Now, in that case if the pressure is P at a point A, here in this figure as shown here, at this particular point, if we consider that what should be the pressure there, if we consider that pressure is P, then this channel if it is the velocity is V, the flow velocity is V, and at the height of this section is Z, and if it is the height from this datum level, if we consider datum level here, then what should be the height? It will be Z plus Z 0, and at this point what should be the velocity head? That will be V square by 2 Z, and what should be the pressure head? That will be P by rho Z, and what will be the elevation head? That will be Z and plus Z 0 from the datum level if you are considering there. So, in this case total head should be summation of these three heads here. So, V square by 2 Z plus P by rho Z plus Z 0. So, by this equation 1 here we can represent the total head, what should be that whenever the fluid will be flowing through the channel with a gravity there. And if the depth of the water channel, if we consider that H in the channel, the water depth is, suppose this one is your water depth. So, here in that case that H should be equal to P by rho Z plus Z, that is the summation of these two head here, that is one is pressure head P by rho Z and plus Z there. So, in this case as a result the total head may be described as follows here. This total head should be equal to V square by 2 Z plus H is nothing but that P by rho Z plus Z and plus Z 0 here. So, by equation 3 we can represent the total head in terms of this water head in the channel along with the velocity head and also the elevation head from the datum label there. And total head relative to the channel bottom, sometimes it will be represented by a specific energy, that is E, represented by E, which expressed the energy per unit weight, and if the cross sectional area of the open channel is represented by A and the discharge then Q, that is capital Q discharge, that will be equal to here, then total energy should be equal to what? E is equal to H plus, this will be Q square by 2 Z A square. So, in this case this total head we are considering that there will be relative to the channel bottom, and this head will be represented by the specific energy E. So, this specific energy that is defined as the energy per unit weight, and if the cross sectional area of the open channel is considered A, then we can have this energy terms here, that is Q square by 2 Z A square. Q is the discharge rate. Now, this relationship is very important, that is given in equation number 4, because for analyzing the flow in an open channel, it is required to sometimes calculate what should be the energy and also what should be the discharge from the channel. So, by this equation, either if you know that discharge, then what should be the energy, or if you know the energy, what should be the discharge from this. Of course, you have to know the water head through the channel there, and that can be easily measured by experiment, and other parts of course Q is known to you and G and A is known to you. So, easily you can calculate what should be the total head relative to the channel bottom or a specific energy that you can calculate from this equation number 4. And if we consider that there is a constant discharge, then what should be the water head that is changed with respect to energy. Now, very interesting that this, if you are changing this energy, you will see there will be a certain relationship of this head with this energy. So, for constant discharge, you will see the relation between the specific energy and the water depth. Water depth as shown in the figure is like this here. So, this line is considered as that the profile for that water depth with the energy there. So, in that case, if we change the discharge rate, then this profile will be changing accordingly there. Other part will be constant here. If the cross sectional area is fixed and of course, gravitational acceleration is constant. So, these parts will be constant, only this thing that this will be changing with respect to this Q square here. Now, if you increase the discharge, then you will see the water depth will be of course increasing accordingly, and if Q discharge rate is decreasing, then water depth in the channel also will be decreasing there. So, we can get a different type of here parabolic relationship with the water depth to the energy here. So, from this profile you will be able to calculate. Now, if energy is so high, in that case there will be a rapid flow. So, that rapid flow condition, you will see there will be a change of water depth, certainly it will be decreasing in that case. So, if you decrease the energy, there will be a certain condition at which you will see there will be optimum value of this energy. So, that is called critical energy, at which you will see what will be the corresponding critical depth of the water in the channel, and for which you are getting this critical energy condition, and you will see there will be a change of behavior of the fluid flow at this condition. So, in that case you will see there will be a change of flow from slower velocity to the certainly jump to the higher velocity. So, at a certain condition where you will see these two velocity will be same. So, at this condition it is called that critical velocity, and beyond this critical velocity you will have this profile of this water depth to the energy here. In this case, before this critical condition, you will see that will be called subcritical flow, or it is called sometimes tranquil flow. And after that, you will see there will be a velocity will be so fast that your energy will be high, and in that case this flow should be in such condition that the behavior it will be like that supercritical condition. So, it will be compared to that air velocity at supercritical condition there. So, we have to design that channel in such way that there should not be certain jump of the flow at a certain condition whenever the fluid is coming out from the channel there. Or if is there any suppose weir you are using that, from the weir the flow whenever it will be coming out from that weir position, there will be a certain change of velocity, and for which you can get that sudden shift of that is water velocity from this critical condition, and because of which it will be called as water jump, or that is called sudden shift of energy from this condition, and because of which there will be a sudden thrust of the fluid on the surface of the wall of the channel, and because of which there will be some abrupt condition of this flow in that case. And also if suppose there will be corrosive fluids are flowing to the channel, then there will be corrosion or erosion of the you can say that wall surface will be there. So, you have to avoid those conditions by obtaining this critical energy condition, and what should be the water depth to be maintained in the channel. So, from this critical condition you will be able to find out. Now, we will see what will be that numerical value for that critical water depth in the channel there. We will be calculating subsequently here. Now, for that critical point, there should be a minimum energy should be required to get this certain change of this flow velocity from minimum to the maximum here. So, that critical point of minimum energy occurs when if we differentiate this total energy with respect to that water height in the channel. So, it is coming when you are considering that dE by dH will be equals to 0. So, what will be that dE by dS? dE by dS is equal to 1 minus q square by g a cube into dA by dH, because this differentiation is obtained from equation number 4. So, after differentiation of equation 4, we are getting this dE by dH that will be equal to 1 minus q square by g a cube into dA by dH, that should be equal to 0 here. So, for this optimum condition or minimum energy requirements, you have to solve these equations for dA by dH. So, this dA by dH will be equal to g a cube by q square. What is dA? A is what? This is cross sectional area of the channel there. So, this cross sectional area will be of course designed in such a way that should be changed to that water depth. So that the total discharge rate will be constant there. So, based on which we are getting this dA by dH will be equal to g a cube by q square, that is as shown in equation number 6. So, from this equation we are having what should be the optimum condition or minimum energy required to get this flow behavior changing from this higher lower velocity to the higher velocity there. In that case, when the channel width at the free surface, if we consider that if it is b, then what should be the dA for that particular point. So, dA should be equal to b into dH. So, the critical area AC and the critical velocity UC, that can be obtained by this equation number 7 and 8 respectively. So, critical area will be equal to what? B q square by g to the power 1 by 3 here. So, this is your critical area. So, dA by dH, you have to substitute the value of dA is equal to b into dH. So, it will come here b will be equals to what is that? G a cube by q square. So, from which what should be the value of AC here? So, AC will be equal to here b q square by g to the power 1 by 3. So, again if you substitute this AC value here in velocity, that velocity should be equals to volumetric flow rate by this critical cross sectional area. So, this critical cross sectional area, if you substitute here, you can obtain this GAC by B to the power 1 by 2. So, from this equation you can calculate what should be the critical velocity and the critical cross sectional area respectively. So, from these two equations we can easily calculate what should be the minimum energy required for which you can get the change of velocity from this channel to its discharge point from a certain weir gun. And then if we consider a rectangular water channel and consider the discharge per unit width is Q. If we consider that there is a discharge per unit width and it is denoted by Q, then we can write here Q should be equal to small q into B as shown in equation number 9. Now, as the sectional area, we know that A will be equal to HB, then the critical water depth HC we can calculate, which makes the specific energy minimum, and that can be represented by this equation number 10 here. So, HC should be equal to Q square by G to the power 1 by 3. So, this is your critical water depth in the channel for which you can get the minimum specific energy, and also for which you can say that at that critical minimum specific energy will be required to change your velocity from this lower to the higher there. And this specific energy or total head in the critical situation, we can say that at this critical water depth HC, then critical energy can be calculated by this equation number 11. If you substitute this HC and Q value there, then you can easily calculate the critical specific energy. And from the previous equation, that is, we can have this what is that Q square will be equals to Z into H cube. Here we have already given that what is the Q value here from this equation number 10. Here we can say that very simple, if we just take the cube of this equation number 10 on both sides, then we can have this AC cube will be equals to Q square by Z, from which you can calculate that Q square will be equals to Z into AC cube. And after substitution of this Q value here in equation number 11, then we can have this EC will be equal to AC by 2 plus AC, then it will be equals to 1.5 into AC. So, very interesting point is that we are having that the specific energy in the critical situation EC will be 1.5 times of the critical water depth AC. So, also if we know this EC at this critical situation, you will be able to calculate what should be the specific energy there for per unit width, and also the discharge per unit also width to be calculated as Q. In that case, what should be the that Q and Q that is critical discharge there you can calculate, and also what should be the critical height also you can calculate. Now, this relationship very interesting that either one you have to calculate. If you know that critical energy, then you can easily calculate what will be the critical depth of the water in the channel. Once you know that critical depth of the channel, then you will be able to calculate what will be the critical area of that. Once you know that critical area and critical depth, then easily you can calculate what should be the discharge rate, the critical discharge rate at that critical situation of this energy. And if we do an example for this, if you are asked to find out the maximum discharge for 2 meter specific energy in an open channel with a rectangular section of 5 meter wide, then you have to use those equations like equation 12 and equation 9 to calculate all those things. Now, maximum discharge, that critical specific energy EC, that will be equal to 1.5 into HC that we have got by this equation number 13 here. So, from this equation number 13, if you calculate this AC as EC by 1.5, then you can get this critical height as per this problem, it will be 1.33 meter. And again, if you use this equation number 12 to calculate the discharge rate per unit width as Q, then Q square is equal to G H cube. From this equation you can calculate this Q will be equal to, then after substitution of this AC value, you can get 4.82 meter square per second. And then after substitution of this Q, small q in equation number 9, then you can calculate this discharge, that will be equal to 24.11 meter cube per second. In this case, this capital Q will be equal to small q into B. This B is known to you, that is 5 meter wide. So, what will be the discharge per unit width? It is calculated from this equation number 12 at this critical height of the water channel based on this critical specific energy. Now, you have to calculate what should be the critical velocity at this minimum energy required for this optimum condition of the channel there. So, the corresponding critical velocity u c or V c, you can say here, it will become as that is V c will be equal to Q by A c. Q is nothing but that discharge per unit width. So, discharge per unit width divided by A c, this will give you the corresponding critical velocity there. So, this it will come as root over G into A c. You have to substitute this here. Q, you know that it is G H cube, and then by divided by A c, then simply you can have this root over G into A c. In the critical condition, then what should be that flow velocity? What should be the flow velocity that will be related to the travelling velocity of the wave? Whenever in the channel there will be fluid will be flowing through certain wave, and that wave velocity, that is called travelling velocity of a wave in a water channel, and that can be obtained if there is a certain depth of smaller from smaller beyond its critical condition. So, in that case you will see after a critical condition beyond this energy, that is minimum energy, you can have this flow velocity in such a way that the velocity will be just considered as a travelling velocity, and the fluid will be moving as a wave. So, in that case wave velocity will be considered as a travelling velocity there. So, in the critical condition, this flow velocity will of course will be same as that travelling velocity of the wave in a water channel, and there will be certain depth, that is of course it will be smaller than this regular velocity in the flow channel. And then at this critical condition, the travelling velocity of the wave in the water channel for that particular depth will be called as a long wave travelling velocity there. And in that case, what should be the critical velocity if you have the critical water depth and the critical velocity there. And when if you know that the water is flowing in an open channel with a flow rate of critical flow rate as 12 meter cube per second, then you have to find out the critical water depth for the channel of rectangular in shape with 4 meter wide. So, in that case critical water depth can be obtained from again the equation number 12 and from equation 9 and also from equation number 14 here. From equation number 12 we have to calculate this AC. AC means critical water depth, that is related with this discharge per unit width Q, and this and then discharge is Q will be equal to small q into B, and V c is given to you here. Now, in this case first of all you have to calculate what will be the small q, because you know this capital Q here and also B here. So, very simple, you can calculate what should be the q and a small q, and after getting this small q you can have this AC just by calculating this V c here, because this V c can be calculated from your that is critical velocity, it is given here root over g h c, and then otherwise you can calculate it from your what is that mass conservation of equation there, and in this way. So, we can calculate here first what should be the, it is given that q, capital Q is given to 12 meter cube per second, and small b is given to you, and also h c, from which you can calculate this q by h c is equal to root over g h c, and it will be equal to what is that, from which you can calculate h c, and what is that V c, then V c will be equal to what, simply root over g h c, and from this then we can have the critical then water velocity at a critical water depth for this critical flow rate of the water for the 4 meter wide rectangular channel. Now, let us consider that flow conditions in the channel before and after the critical condition. Now, before the critical conditions, the flow behavior will be represented by this supercritical, and beyond this it will be supercritical flow. Now, when and how that will be defined, you just see this video here, you will see how this whenever liquid is flowing through the channel, you will see there will be an object that is some obstruction by a what is that circular stone, and over which that flow is flowing, and before this point you will see there will be a depth of water channel will be there, it will be represented by H, and at that condition of critical condition where from this stone you will see the flow will be suddenly drop to its higher velocity there, where this H that water depth will be smaller than other part. So, in this case if their H is greater than H c, it will be called as subcritical, and when H is equal to H c, that will be your what is that critical condition. If H is less than H c, it will be called as supercritical condition. Now, this is very interesting, this phenomena is sometimes it is called that hydraulic jump. We will come to that point, hydraulic jump. So, from this figure we are observing that whenever fluid is flowing through the channel at this condition here, at this condition the water depth will be higher and the flow velocity will be is less than this critical velocity, and after this your critical condition you will see the water depth will be lower, whereas the velocity will be greater than the critical velocity, and at this critical condition both the height will be considered the critical height and velocity should be the travelling velocity of the wavelength there. So, if the flow depth is deeper or you can say that shallower than H c, the flow behavior will be different whenever fluid will be flowing through the channel. Now, when the water is deeper than H c, the velocity is smaller than the travelling velocity of the long wave, and this type of flow will be called as tranquil or subcritical flow. And if the water depth is shallower or smaller than the H c, then the velocity is larger than the travelling velocity of the long wave that is produced after this critical condition, and this type of flow is called the rapid or you can say supercritical flow. Now, as shown in figure here, the profile of this water depth to this discharge rate per unit width is given. This profile, if you show that at this height, at the maximum height, you will see there will be a that is here this minimum flow rate, and in that case the energy should be higher, and also in that case the liquid height will be lower in that case, and also you will see at this critical condition this where Q max will be there, in that case there will be a condition from which you can get the separation of this supercritical and subcritical flow or tranquil or rapid flow there. So, this relationship will give you at exactly what location that you can get this critical flow condition of the channel flow. And very interesting that we have already obtained that AC should be equal to 2 by 3 E or E should be equal to 1.5 of critical what is that water depth there in the channel. So, up to this is your Q maximum will be obtained at this what is that critical water depth there. Now, if we consider the case where the rectangular water channel from equation number 4 and 11, we can express this energy per unit that is depth of water channel, then it will be represented by this equation number 15 as E by H will be equal to 1 plus Q square by 2 G H cube. Now, this specific energy it will increase parabolically as shown in the figure here from 1 with Q small q, and you will see when this water depth is critical at that condition. So, at critical condition, if we plot this E by H versus Q by root over G H cube, we are getting this parabolic shape of this nature of flow characteristics. So, in this case, if this Q square will be equal to G H cube, then you can have this E by H will be equal to 1.5. So, here this is your E by H, this is 1.5, and where this Q square will be equal to G H cube. So, from which you can calculate. Similarly, if you change this Q value, then if it is coming as Q will be equals to 2 into root over G H cube, then you can have this value of E by H will be equals to double of this critical water depth. So, if you increase the double of this Q, then immediately you can calculate what should be the critical water depth in the channel from this relationship. Now, if we consider an open channel with rectangular cross sections of 3 meter wide and 15 meter cube per second of water is flowing at 1.2 meter depth of water. Now, you have to say that is the flow rapid or tranquil, and what is the specific energies there. And we know that from equation number 12 that we have discussed that AC should be equal to Q square by G, that should be to the power 1 by 3, and from this equation you can calculate what should be the AC. For this you need to the value of discharge per unit width, because unit width is given to you, from which you can calculate here Q, then Q is equal to capital Q by B, this will be your discharge per unit width. So, this Q will be as 5 meter square per second here, and from equation number 15 then you can calculate this E by H. If you know this AC value you can calculate from equation number 12 after substitution of value of small q there. And if you substitute again this q value small q and AC from this equation number 12, then you can have this AC will be equal to 0.85 and also respective U will be equal to 2.083. Now, in this case water depth is 1.2 and it is deeper than AC we are having, because AC we have calculated from this equation number 12 as 0.85, whereas water depth is given as per this problem it is 1.2 meter. So, this 1.2 meter of course, it is greater than this critical depth. So, we can say that the flow the velocity is smaller than the travelling velocity of the long wave, and then we can say that as per definition that the flow will be tranquil, or you can say that it will be subcritical flow. So, based on this example we will be able to calculate whether the velocity will be subcritical or supercritical. Now, let us have an discussion of hydraulic jump here. Already you have seen this video here. What is that? Whenever fluid will be flowing through the channel, and if it is coming out from a certain flow obstruction, then you will see there will be a regular flow obstruction, of course, maybe wear or some other that is surface over which this flow will be overflow, and in that case the flow, whenever it will be flowing over this surface, and there will be certain jump of this velocity, or you can say fluid mass into the channel of this remaining part, then this phenomena you will observe as shown of this video. So, it is a phenomena, you can say that flow when the liquid at high velocity that will discharges into a zone of lower velocity, and a rather abrupt rise occurs in the liquid surface there. And you will see, and here in the here it is the phenomena where this is your higher velocity, high velocity, where in this region it will be lower velocity, whereas here in this video it will be your lower velocity, and here in this position it will be your higher velocity, again it will gain, and here lower velocity there. So, in this case there will be a creation of some phenomena that it will be called as that hydraulic jump is there. So, you will see in this video, in this picture also, there will be certain jump of this liquid, and it falls and hits at the surface, and after that the fluid is getting its velocity that will be lower than this here. And then rapid, you are observing that there will be certain rapid flow, and which will be very unstable, and if it is decelerated, and then it suddenly shifts to its subcritical flow. So, there are two flow phenomena here, one is lower velocity, another is higher velocity, and there will be some critical velocity there. So, the velocity lower than critical velocity, it will be called as subcritical flow, and if it is greater than that critical velocity, it will be supercritical flow. So, the hydraulic jump, it is a phenomena of the flow when the liquid at high velocity discharges or low velocity discharges into a zone of lower velocity or the higher velocity. That is two ways it can happen as shown in figure here. So, a rather abrupt rise occurs in the liquid surface is there. So, this phenomena will be called as hydraulic jump. Now, this hydraulic jump of course, will be coming as that based on that critical flow condition here. So, when the inclination of a dam bottom is suppose deep or steep, you can say the flow will be very rapid. So, in that case it will be a supercritical flow, and when the inclination becomes gentle downstream for a dam, the flow is unable to maintain rapid flow, and it suddenly shifts to subcritical flow there. So, it is important to say that there you will see whenever the fluid is coming from a higher position, higher water depth to the lower water depth there, you will see there will be a certain change of energy, and that energy will convert it to the what is that maybe elevation energy or static energy to be converted to the velocity energies there. So, that energy sometimes it will damage the bottom surface of the channel, and because of which you have to get an idea when that optimum condition, or how to avoid or how to design the channel surface in such a way that at that critical high energy of that velocity that is energy conversion from this potential to the velocity head or velocity energy, and by which you can of course design the channel there. So, here as shown in figure, very interesting that the designing of that dam or channel, that you have to make the inclination of that dam bottom whether it should be steep or not. So, if it is very steep, then the flow will be rapid, and if it is very gentle downstream, then the flow is unable to maintain rapid flow, and subsequently or suddenly you can say shifts to the subcritical flow. So, there is a jump. So, you have to maintain that critical condition where that this change is happened at that critical water depth to be maintained to get this optimum condition of channel design. And what should be that wave velocity during the hydraulic jump? The travelling velocity of that long wave after this critical condition, it will be of the small depth of h of the water channel, and then it will be calculated as here root over g into h. So, this will be represented as travelling velocity of the long wave, and the ratio of this flow velocity to the travelling velocity, it will be represented by a dimensionless number. It will be called as Froude number. So, Froude number, very interesting that here long wave velocity, what should be that, whether it should be higher than the long wave velocity, travelling velocity higher than the flow velocity or not, based on this Froude number. If Froude number is equal to 1, then you can say that subcritical flow will be less than 1. In that case, of course, the critical condition you can obtain, that means here Froude number, if it is suppose travelling velocity is less than, suppose Froude number is equal to, if Froude number is equal to 1, then of course, V travelling will be equal to V flow, flow velocity is there. So, both will be same, that is that critical condition. If it is less than 1, if it is less than 1, then of course, this travelling velocity should be, what is that, less than flow velocity. So, it will be coming at this subcritical condition. So, subcritical condition, when again if it is greater than 1, of course, it will be that flow velocity will be, or travelling velocity will be greater than this flow velocity. So, in that case you can have this supercritical flow. Now, of course, that supercritical flow will not be the actually there the desirable condition. So, Froude number should be always less than 1 in that condition. So, that you can get the subcritical flow condition whenever you are designing the dam there. Now, if the flow velocity is smaller than the wave velocity, then it will be called as subsonic or supersonic also. So, the Froude number of the rapid flow is larger than 1 for the subsonic or supersonic flow. In that case, the flow velocity is larger than the wave velocity, thus the subcritical flow and the rapid flow in a water channel correspond to subsonic or supersonic flow respectively of a compressible gas. So, here this subcritical will be represented by this subsonic, and rapid flow or supercritical it will be as supersonic flow there. And in that case, you will see there will be a certain analogy between the hydraulic jump and the shock wave. For the flow of gas in a convergent divergent nozzle, the supersonic flow which has gone through the nozzle space, if you are considering one nozzle, then you will see that in this figure here, flow is coming from this position to this position and then this position. So, in this case, here velocity will be higher, whereas in this section velocity will be in this position velocity will be lower, and in this position velocity will be higher, whereas in this position again it will be lower. So, it will be what is that subsonic, it will be supersonic, and it will be what is that subsonic again. So, it is analogous to this convergent divergent nozzle flow. If the back pressure is high in this case, then the flow certainly shifts to the subsonic flow with a shock wave there. So, it depends on that how much pressure is creating over there. So, the flow certainly shifts to the subsonic flow if it is here. In this case, from this supercritical flow, again certainly after jumping it will do that subsonic flow, then at this condition it will be considered as a shock wave is there. So, we can have this hydraulic jump as per that convergent divergent nozzle flow there. So, in that case only thing is that whether it should be subcritical or subsonic or supercritical or supersonic, or what are this critical or sonic. So, this analogy will be maintained or you can consider in that case of this channel. Now, why to know this hydraulic jump phenomena? That interesting that you have to always remember that when a hydraulic jump is brought about, energy is dissipated by it, thus the erosion of the channel bottom can be prevented based on this idea of this hydraulic jump phenomena. In that case, when this critical flow will be happen and at which water depth this critical flow will be happen, and when this subsonic, when this supersonic or subcritical or supercritical flow will happen, that you have to calculate based on this formula that here discussed. So, I think you have learned something about this, what is that hydraulic jump and this supercritical subcritical flows, and what is the analogy, and also how to calculate the water depth, critical water depth, and also what should be the critical cross sectional area for the design, what would be the energy required, so that you can have the idea to prevent the erosion by certain what is that thrust of the water by rapid flow in the water channel, whenever it will be flowing is coming out from this lower velocity to the higher velocity zone. So, for further reading I can suggest this again these books for better understanding of course, and this is the basic things that we have discussed here. I think from this basic knowledge you can calculate, or you can have certain interpretation and also the knowledge by which you can go further for a design of this flow device based on this fluid flow. So, thank you for this lecture.